Hi, I'm Doma from Arizona State University. I'm sorry I couldn't be there to present our poster in person due to the visa issue. Let's start with why I developed open foundation model from numerous public datasets using their heterogeneous expert annotation. Deep learning nowadays offers expert level performance and sometimes even super expert level performance. But achieving such performance demands massive annotated data for training. For example, Google's CXR foundation model was trained with over 800,000 labeled, mostly private chest X-rays using supervised contrastive learning. With only API released, this foundation model can serve as a feature extractor but cannot be fine-tuned. In medical imaging, there are numerous public datasets available from global sources. They are individually small, but together they can be add up to a great amount. Can we train an open foundation model using expert labels associated with these public datasets in supervised fashion? Because aggregating public dataset costs nearly nothing, but enlarges data size, diversifies patient population, and accrues knowledge from diverse experts. Therefore, we envision a powerful and robust foundation models can be trained from numerous public datasets. But the challenge is datasets annotated from different institutions try to be annotated differently, even when addressing the same clinical issue. So this research is to address this challenge, how to utilize multi-sourced datasets and their heterogeneous expert annotation to pre-train foundation models. To this end, we have developed a framework called ARC that trains foundation models with numerous public datasets by accruing and reusing knowledge from their heterogeneous labels. Our ARC is built on a student-teacher model with multitask heads via cyclic pre-training. It first accrues knowledge into the student via cyclic pre-training. At each iteration, the student aims to accrue the expert knowledge through its corresponding task head by sequentially scanning all the data sets one by one in one epoch. Then the accrued knowledge in the students is accumulated into the teacher by exponential moving average. Then the knowledge in the student can be reused to accrue more knowledge from the next task. Finally, to reinforce such feedback loop between student and teacher, we incorporate a consistency loss to reuse the knowledge from the teacher as a self-supervisory signal to facilitate the transfer from historical knowledge in the teacher to the student as a reminder to mitigate forgetting. After pre-training, the teacher model, the pre-trained teacher model can be reused for transfer learning by fine-tuning, or it can serve as a feature extractor by linear probing. So with this framework, our ARC is knowledge-centric, label-agnostic, task scalable, and annotation heterogeneous, and the result shows its application versatile. To demonstrate our ARC's capabilities, we have pre-trained two ARC models, ARC5 from the first 5 datasets, and ARC6 from the first 6 datasets. We evaluate them and compare them with the state-of-the-art fully supervised and self-supervised method, particularly a self-supervised domain-adapted model, which is pre-trained using 926,000 CXRs. So our fine-tuning results shows ARC significantly outperformed the SOTA method on both various thoracic disease classification tasks as well as the organ or bone segmentation tasks, showing our ARC is more transferable and generalizable. In fact, when compared with this self-supervised domain adaptive model, ARC wins with less pre-training data. This actually highlights the importance of learning from the expert label compared to learning from self-supervised label. Now, let's look at the comparison between our ARC model with Google's CXR Foundation model. Our linear probing results shows ARC embedding can achieve a consistently superior or at least comparable performance as compared with Google CXR Foundation model, showing ARC offers higher quality embeddings. In the scenario of small data or limited data, for example, the few shot evaluation, ARC actually exhibits much better performance than CXR Foundation models. For example, here with only 20 ARC6 embedding, it can achieve nearly 96% of the full performance, which is attained by using over 10,000 embeddings for training. Moreover, with 30 ARC6 embedding, the performance can surpass the Google's embedding with using 533 embeddings. Next, in terms of model's robustness, our ARC shows lower false negative rates, indicating a better under-diagnosis mitigation. And also, our ARC demonstrates a strong, robust, or resilient to gender imbalanced data. Gender bias here is categorized by significant drop in performance when training and testing data are of opposite gender, compared with when they are the same gender. For example, here, the blue boxes indicating the results you trained using male split from CXR Foundation models embedding, and it tested in the female patient. So this is the significant drop compared with when training on female split and testing in female patient. So that's the same gender. So each green circle here indicates a lung disease that with gender bias by CXR Foundation model, where our ARC exhibits more robust performance, showing no significant difference. So despite our ARC using less pre-training data and has a much smaller backbone, ARC exhibits better performance than CXR Foundation model. This underscores the importance to learn from more detailed labels, more granular diagnostic labels, compared with that Google's model uses coarsened normal or abnormal labels. To conclude, our ARC model, in our work, we propose ARC Foundation ARC that realize our vision of cruising and reusing knowledge with numerous public data sets using their heterogeneous expert annotation. This can achieve superior and robust performance. Our ARC's performance is strong on chest X-ray, and we are extending it to other modalities. ARC's performance is inspiring, and we hope it can encourage researchers to share code and dataset for creating open foundation models, accelerating open science, and democratizing deep learning for medical imaging. Thanks for listening.